software. All right. Well, everybody, thank you so much for joining us today. I'm very excited to have Mr. Jackson Stansel from Sentinel Ag here to present on Beyond the Field Plan, Scaling Integrated Water and Nitrogen Management Where It Matters. I've had the great pleasure of working with Mr. Stansel before and learning about nitrogen management on some trips and at conferences, so I'm really excited that he's here to share with us today. Just a few housekeeping rules. We'd just like to ask that you keep yourself muted unless you have a question. If you do have a question at any time during the presentation, feel free to type it out in the chat. I'll be monitoring the whole time, so I'll be able to let our speaker know and we can address it that way. You can also use the raise hand feature on Zoom, or you can just wait until the end and we can address any questions you have then. But with that being said, Jackson, I'll hand it over to you.
Awesome. Well, thank you very much, Lane, for having us and for making that introduction. And I appreciate all of you who have taken the time to join us here today. We are going to be talking about going beyond the field plan today, and specifically how scaling integrated water and nitrogen management can help us do that. I'll give a little bit of background on Sentinel Ag, where we come from, why we exist. I'll talk about what we offer, and then I'll get into a few case studies and practical implementations of our technology toward the end of the presentation today. I do hope that there will be some questions. I see some names that I'm familiar with in the participant group, and also some that I'm not familiar with. So I'm excited to answer some questions today. All right, so diving into today's presentation, Sentinel Ag is the name of our business. We were founded to really focus on providing solutions that improve farm profitability and land stewardship. We've been around for almost 5 years now. We were founded in 2021 based on technology that I contributed to developing at the University of Nebraska as a graduate student in agricultural engineering there. Nebraska still remains our business's primary focus. In a lot of ways, it is definitely our core market, but we have expanded far beyond that, as you can see on the map. We have enrollment today in 25 US states in our platform, plus we have enrollment in Brazil and New Zealand. So this technology has been widely adapted and utilized across different geographies. We currently serve farms through our Sentry network of certified service providers. I'll get into a little bit more detail about that later. But we currently have 56 of these certified service providers that span 12 states here in the US, and we're working on developing those certified service providers internationally as well. One of the big reasons why Sentinel Ag was started, as well as why the original research behind the technology that we use today started, was Nebraska's nitrate issues. Many of you may be aware that nitrate contamination of groundwater is a primary concern, especially in areas that have significant amounts of irrigated agriculture. Nebraska is certainly no stranger to nitrate contamination in groundwater, and in many ways, Nebraska has taken a lead in terms of addressing this particular challenge because of how dependent the state is on groundwater. If you look at the maps that are shown here over on the left-hand side of the screen, you can see where nitrate contamination in groundwater is most prevalent in Nebraska. If you look at the primary river that is running through the middle of the state, that's the Platte River there. You can see that there is a lot of nitrate contamination, those red dots that are shown along the river there. And these are heavily irrigated areas of agriculture as well. And then along the Elkhorn River and other river systems throughout the state, you also see that there is high concentration of nitrates in the groundwater. Some of you may be aware Nebraska has multiple different phased areas with different requirements for nitrogen and irrigation management. As a result of these nitrate issues, we have been collaborating with multiple NRDs in the state of Nebraska to equip growers with solutions that can help to mitigate nitrate contamination of the groundwater. And we've been working with the State Water Quality Task Force to define some action plans around this. But really the idea for our technology and part of the impetus of it being developed at the University of Nebraska was to equip growers proactively with solutions to this problem that help us to improve farm outcomes, so keeping farms productive and profitable, and also limiting any sort of punitive or regulatory measures that may have to be taken to address this concern if steps are not taken in this proactive manner. This is not just a Nebraska issue, though. This is really a nationwide, and I would argue even an international issue. If you look at the map of irrigated acres in the U.S. and then the map that's been produced by the USGS predicting nitrate in groundwater, you can see that irrigation concentration is generally highly correlated with nitrate contamination in groundwater. It is part of the factor is just the aquifer accessibility, right? But part of it is also the intensity of agriculture and the input requirements that are necessary to achieve the productivity gains that are necessary to make irrigated agriculture a profitable enterprise. Collectively, this is just one of the concerns that farmers are facing when it comes to input management, specifically when it comes to nitrogen. Right now, farmers internationally are leaving about $200 billion on the table every year. We've seen that there are really three things that are driving a lot of the challenges farmers are facing when it comes to nitrogen management. Market dynamics are one of those. We've seen that fertilizer prices are incredibly volatile between COVID and now the Middle Eastern conflict that we're seeing in the news today. There have been multiple price shocks since 2021. Fertilizer access is a major concern for farmers this year. Possibly not enough domestic production to meet demands, and a lot of farmers are concerned about even being able to get the fertilizer that they need. And on top of this, we have low crop prices. So farmers are getting crunched between low crop prices, high input costs, and profit is really a struggle. Policy is part of what I've already talked about today around nitrate contamination of groundwater. We're seeing policies enacted to deal with this groundwater nitrate contamination, including in Minnesota, for example, where they have a groundwater protection rule. We're seeing limitations imposed on fertilizer and water usage in certain resource districts in Nebraska and in other places around the U.S., as well as in New Zealand and other countries around the world. We're also seeing that there are market expectations that are arising for products that have reduced waste and contamination. Overall, this comes full circle at the farm and the fact that agronomy for nitrogen and water is really challenging. Yield potential is a moving target every year as a result of weather volatility. That same weather volatility is increasing over time and really erodes how much planting can impact and actually sustain itself throughout the course of the growing season. Nitrogen is largely invisible, so it's hard to keep up with in the field and ensure that it is available in the right form for the crop to take up. We're also seeing that there's increased adoption of alternative products and regenerative practices, which change input dynamics for nitrogen and water. So all of this comes together to say that with the price of fertilizer and the challenges that are associated with managing inputs, bad input decisions have really never been more costly than they are today. A great example of why planning and developing a field plan is just not a sufficient solution today is the Nebraska nitrogen algorithm. This is a good algorithm that translates quite well in most cases. And it is very similar to what other states have put in place for recommending nitrogen in agricultural production. But what I want to call out is that almost every part of this algorithm is environmental condition dependent. And what I mean by that is it's dependent upon temperature, rainfall, as well as how management intersects with those environmental conditions. Looking at this algorithm, it basically takes into account estimated yield, which is this EY here, the nitrogen that's available in the soil, the soil organic matter, and then other credits that are potentially included within the algorithm. These other credits can include manure, previous crops, and irrigation nitrates. The challenge is that all of those factors and how those different sources of nitrogen turn into plant available nitrogen are incredibly dependent upon temperature, moisture, soil pH, and other things that are really highly dynamic. There are also a couple of other condition dependent factors even outside of these other credits. For example, your estimated yield, which is basically your yield potential every year that is incredibly weather dependent, and your mineralization rate, which is this 0.14 scalar here, is also temperature and moisture dependent. The bottom line here is that everything will change during the growing season with how these different factors that are contributing to nitrogen availability are occurring. And they'll also change between growing seasons, right? So it's really hard to anticipate what exactly am I going to get in the upcoming growing season. So adjusting to these conditions in real time during the growing season, just it's not only an option anymore, it is absolutely essential to getting nitrogen right. That's why we built the Sentinel platform. The Sentinel platform is a software platform that integrates satellite imagery and multiple other data sources to help provide decision support for nitrogen and water application timing, amount, and placement. There are 4 tiers to the platform that are each geared to different use cases. We have our Sentinel standard tier, which is simplified nitrogen management that's built for dryland row crops. We have our Sentinel irrigation tier, which is standalone irrigation insights specifically for not non-nitrogen intensive row crops. So think soybeans, for example. Sentinel Advanced is advanced nitrogen management for in-season precision. This is really our most popular tier and the one that we have gone to market with since the beginning of our company. And this is really geared for irrigated, intensive nitrogen management. Sentinel Complete is our newest tier of the platform, and this integrates our Sentinel Irrigation tier and our Sentinel Advanced tier to provide integrated nitrogen and water management. And this is also a really great fit for those intensively managed irrigated acres. This platform is built to address multiple different crops. We have most of our experience in corn production, but we also are gaining a lot of experience right now in cotton, small grains, potatoes, and forages. So it really is built to be dynamic and adaptive to these different cropping systems. And it's also built to solve many of the challenges that are faced at the farm level and by agronomists that are supporting those farms. We think that's absolutely critical to talk about because ultimately, if the solution is not usable at the farm level, it's not going to be widely adopted. Some of what makes this platform easily adoptable is that it doesn't require any hardware or labor. It has very quick field setup. We describe it as sub-minute field setup, as in you can set up an entire field in less than a minute. We do provide daily site-specific insights, so it's high-frequency data, and we are providing data across the full field, so you're never going without the full picture. And lastly, it does not require a yield goal, so we're not operating off of that estimated yield like I talked about with the Nebraska nitrogen algorithm, but instead we are dynamically adjusting to environmental conditions and to the yield potential in the field with our recommendations. Some of the specific capabilities that the Sentinel platform offers are detecting demand. We track nitrogen sufficiency of the crop over time, detect when the crop is getting hungry for additional nitrogen, and help you to apply before that hunger actually impacts crop yield potential. This is all about getting timing right, which we know is imperative for crop production. We also have our all-in advisor tool, which helps to adjust rates and inform placement of where fertilizer is going in the field. This all-in advisor tool incorporates weather history, weather forecasts, crop data, and our proprietary modeling technologies to provide rate recommendations that are specific to this particular season and that particular crop and how it's been managed in that season. This all-in advisor tool fuses with imagery to allow us to target specific areas in the field that may need more or less nitrogen so that we can achieve those specific needs, but also potentially save some money by getting nitrogen into the right places in the field. And even if we're not saving money, better allocate where that money is going in the field and making sure that any dollar spent is going to be a dollar that is turned into crop utilization. Lastly, we have our hydroflow insights, which help to identify risk. We know that wet conditions can create a risk of nitrogen loss, whether that is leaching through the soil profile, or whether that is volatilization or denitrification that's resulting in atmospheric losses of nitrogen. By monitoring soil moisture through the field, both at a field level and spatially, we're able to assess the risk of loss events, most particularly leaching conditions and saturated conditions in the soil. So that is a really important capability within the platform as well. To dig into that a little bit more, what we are currently doing is pulling in remote sensing data that assesses surface soil moisture, applies soil properties to that surface soil moisture, and ultimately applies a hydrologic model to track soil moisture conditions across the field spatially, as well as in different soil profile depths over time. We're able to do a hindcast, current condition, and forecast for the soil moisture variable, and we're able to assess leaching risk as a function of all these different factors. This leaching potential forecast and these spatial maps can be used to inform decisions about whether or not to irrigate, given the chances of leaching at an individual point in time. Can also be used to inform scouting. So if an agronomist wants to go out into the field and see, is there actually leaching going on in these locations? It can also be used to inform probe location within the field. So where do we want to place soil moisture probes? And lastly, it can also be used to inform nitrogen application timing. So there are a lot of different ways that this can be used. If you look at this at a watershed level, it can also be used to assess watershed level risk of leaching events that could contribute to groundwater nitrate contamination. Some of the use cases that we've seen for this technology are, number one, agronomy. This is just the sufficiency tracking, demand detection, and really all of the decision making that goes into controlling nitrogen and water inputs on the farm. We've also seen this be used to facilitate practice changes. We're seeing a lot of uptake and adoption of regenerative systems, especially as farmers look to separate themselves a little bit more from the supply chains that are creating really high input costs and creating access limitations for them. These practices may include cover crops, manure and livestock integration, whether that is just applying manure coming from a neighboring farm or from actually grazing livestock on crops, whether those are covers or crop stubble. And we're also seeing tillage reduction used as a practice change. And this doesn't even really include the alternative products that we're seeing being used, from biologicals to biostimulants and alternative fertilizer formulations. All of these different practice changes create new dynamics for nitrogen credits. And ultimately, we're seeing that the real-time data and advanced modeling in our technology are able to help producers make good risk limiting management decisions while they are adopting these new practices. So again, this technology can be used to facilitate practice changes. A third element of this is program management. We have dashboards, enrollment reporting, agronomy insights, proactive notifications, and scalable reporting within our platform. And we've seen that all these can be used to help enhance program measurement efforts. So that is another key use case within this technology. This technology has produced consistent results, specifically on corn. Over the last 4 commercial growing seasons, we've consistently seen between a 0.7 and 0.8 NUE, which is pounds of nitrogen per bushel of grain produced. This has basically come from nitrogen reductions while maintaining or improving yields. Those nitrogen reductions have consistently been between 40 and 50 pounds of nitrogen per acre, and they've resulted in nitrogen-specific savings of $27 to $40 per acre on the farm. Across the last 4 years, we've seen an average increase in yield versus expectation of 4 bushels per acre, which has ultimately translated to about a $59 per acre average profitability improvement on the farm. And across the last 4 years, we've seen a 6.4 million pound reduction in nitrogen application on the acres that we have served. To break that down even a little bit further, because we know that this is a target for many different entities right now, this nitrogen reduction concept, 59% of the fields that we have served have been able to reduce nitrogen by more than 40 pounds of nitrogen per acre. We've seen that 82% of fields have been able to reduce by 20 pounds or more per acre. So that's a really good indication that nitrogen reduction is possible on the vast majority of acres. On the flip side, we've also seen that 4% of fields have needed to increase nitrogen applications to hit their productivity and profitability targets. Overall, this has meant that we've had a change range in nitrogen fertilizer of about 205 pounds of nitrogen per acre, with our largest increase being 81 pounds of nitrogen per acre versus grower standard practice, and our largest decrease being 124 pounds of nitrogen per acre versus grower standard practice. This is on the commercial side. We also benchmark our technology each year in replicated trials against farmer practice in actual production environments. And we've seen a $22 per acre profitability improvement there, even against very proactive and progressive growers. We've seen a 23% efficiency improvement and a nitrogen reduction average of 50 pounds of nitrogen per acre. Overall, this results in a trial-based ROI on the system cost of 150%. So it's a really good net ROI on the system. If you look at gross ROI, this is more like 250%, and that's just using our trial-based data. To start looking at maybe how this technology is actually applied farm to farm, this particular field that we had in the system in 2024 is a great example of how this technology can be used. This field was planted in early May. This is a cornfield in west central Nebraska. From the time that the crop was planted until mid-June, there was a high leaching risk that was detected based on soil moisture modeling. This leaching risk was maintained near or above 50% throughout that entire interval, and we saw that there was a clear crop development lag within the optical imagery that we received over that time. If you look in the bottom right-hand corner, you'll see your soil water content graph here. The blue is the nearing saturation area, and anything above that is basically in a saturated condition. And you can see that we were either nearing saturation or saturated throughout this entire period, which is definitely an indicator of a high leaching risk on this particular field. By the time we get to mid-June and our optical imagery has enough biomass in the field to read from the satellites, we had detected a deficiency in nitrogen. This deficiency in nitrogen detection led to an application of nitrogen, and we had multiple applications of nitrogen that occurred because we continued to detect a deficiency in this field. The sufficiency index trend line, shown over here in the bottom left-hand corner of the screen, shows that there is a response following these applications. For example, this green triangle here, the positive response that is made within these two zones following that application. We also show a slower response after these later biological applications that were made. So first two were traditional fertilizer, the second two were biological. So this is a slower response shown in that sufficiency index with those different fertilizer sources. After the last application, the crop was able to stay in the optimal zone, which is the green part of the sufficiency index trend line from R1 and beyond. So all the way through crop maturity. So this is an example of how integrating soil moisture tracking and crop nitrogen sufficiency tracking can lead to very holistic and integrated water and nitrogen management. Implementation of the system is really easy. We really believe that verifying and validating remote sensing data is critical, so that's part of what we'll do, and I'll talk a little bit about the technique that we use to do that on the next slide. But to get started implementing the technology, we need a field boundary. These can be drawn in the system, they can be uploaded from a shapefile, they can be entered with a legal description or found with a legal description and then drawn within the system. From there, you just need to enter your crop plan. So that would be your planting date, your anticipated maturity of the crop that you're growing, and at what density you're going to be seeding that crop, and then any sort of nitrogen applications that you're anticipating for that year. Pretty basic crop planning information. From there, you would choose a calibration method. We do have our Sentinel plot calibration method, which I'll talk about on the next slide, which is the recommended approach that we have to the system. We also have a plotless calibration technique that ultimately makes it even easier to start using the platform. From there, you just need to confirm your planting and application info as you go throughout the growing season. And we will provide notifications and recommendations from that point on as we are monitoring and recommending interventions on the field. With those notifications and recommendations, it's really just up to the end user to act decisively with the information that's been provided through the platform. I did mention our Sentinel plots on the last slide. One of the biggest things that we worked on, and one of the biggest challenges with image-based nitrogen management technologies in the past, has been the fact that it's very difficult to isolate what is creating differences and crop reflectance in different parts of the field. That makes it really challenging to say whether or not nitrogen is really your yield limiting factor and to make recommendations on nitrogen. That's what we've solved with our technology and with our Sentinel plots. These Sentinel plots are paired nitrogen poor and nitrogen rich plots that go out into the field with an early season fertilizer application. For example, if a farmer is putting on 100 pounds of nitrogen per acre around planting, we would ask them to reduce that nitrogen rate in certain locations by about 30 pounds of nitrogen per acre in corn, and to increase that nitrogen amount by 60 pounds of nitrogen per acre in other locations for a corn crop. What these plots allow us to do are to isolate the impact of nitrogen on crop performance, to assess yield potential, that's particularly our nitrogen rich plot or our reference. Because it has more nitrogen on it, we can see is that additional nitrogen helping to drive yield potential forward by improving crop vigor. Our nitrogen poor plot, or our canary, also helps to warn of upcoming demand in the crop so that we can stay ahead of those crop needs and continue pursuing that yield potential that's in the field. Our software is built to make this easy. We offer automated zone creation so that we can say which parts of the field need to have these plots in them so that we can isolate the impact of nitrogen in those different areas. We also offer automated plot placement and automated prescription building through the platform so that really this entire process can be done automatically with almost no effort from the end user. We also have QA/QC tools, redundancy, and user editing tools built in to the platform so that we can be confident that these plots are going out correctly and being used correctly to calibrate imagery throughout the course of the growing season. Lastly, the system is also built to be scalable. I mentioned earlier that we offer dashboards within the system. We also offer a fields list with a map view so that you can spatially see how fields are performing. Everything in the platform is built to be stoplight simple, meaning green is good, yellow is caution, and red means that you really need to give it your full attention. So it is really easy to interpret what is going on in the platform and direct your attention to where it needs to be directed to the most. Okay, now that I've talked about the platform, I want to get into a few examples of how this technology has been used and a few case studies showing its performance. I'll highlight just a few different use cases. This one in particular is rain-fed corn in Illinois. The particular use case that we had here is the grower wanted to side dress nitrogen about 30 days after planting. This crop was planted on May 8th. Nitrogen was applied immediately thereafter on May 9th. And on June 10th, the grower went out to side dress. On this date, we recommended 70 pounds of nitrogen per acre. The grower's typical rate was 115 pounds of nitrogen per acre. Both of these rates were run in strips in the field. Ultimately, Sentinel yielded as well as the grower, actually a little bit over, but in this case, there really was no major difference, while reducing applied nitrogen by 45 pounds and improving profitability on this farm by $35.50 per acre. Additionally, there was less nitrogen stored in the soil and less nitrogen exposed to risk of loss, whether via leaching or denitrification, which ultimately is a good thing for the environment as well. I'd also like to highlight an irrigated corn use case, this one from Shorter, Alabama. This particular field was planted on March 25th of 2025. It was under irrigation, as I mentioned. In this particular case, the field was started with about 110 pounds of nitrogen per acre prior to any Sentinel recommendations. On May 1st, there was an application made at side dress. We recommended only 30 pounds be applied at this point, and the grower's standard practice was 120 pounds of nitrogen per acre. We continued to monitor the field to see if there was additional nitrogen demand, and ultimately determined that there was not additional nitrogen demand on this field. And so we reduced the overall applied nitrogen by 90 pounds of nitrogen per acre while having a similar yield to the grower. There was a 1 bushel per acre difference. And this resulted in about a $55 per acre improvement in profitability. So Moving from rain-fed corn to irrigated corn, you can see a very similar use case in informing a side dress rate, and a very similar outcome, reducing nitrogen that is stored in the environment exposed to leaching loss while also improving farm profitability. The next one I want to show is fertigated corn. This comes from Albion, Nebraska, planted on April 16th of 2025. This particular field received 12 pounds of nitrogen per acre at planting, and then 60 pounds and 48 pounds were applied via fertigation on two separate dates, June 11th and June 30th, to all the sectors in the field. And then on July 14th, there were 45 pounds of nitrogen per acre that were applied just to the grower sectors in the field via fertigation. At that point, Sentinel determined there was no additional nitrogen demand and no need to fertigate on our sectors. Ultimately, Sentinel produced a yield that was right there with the growers, in this case, 3 bushels per acre higher, while reducing nitrogen, again, by 45 pounds of nitrogen per acre and improving profitability by $44.50 per acre. So another example here of limiting the nitrogen that's put into the environment unnecessarily while also improving farm profitability. And lastly, I will indicate that we are operating in other crops and we have seen success in other crops. Potatoes are one of those that we are working on quite heavily right now because we know that they are actively fertigated and intensively managed under irrigation. A potato trial that we had a couple of years ago showed that the Sentinel rate was able to produce at least as many potatoes within the target category as the grower. In this case, we actually did recommend that more nitrogen was applied to the potatoes and what the grower traditionally would have put on. And we saw that the Sentinel treatment had close to the highest FL solids in the potato crop as well. We've seen that our imagery has been able to track different growth stages of a potato crop. We've also been able to track nitrogen response in the potato crop as a whole, as well as in different zones of the field. So the technology does translate to other crops like potatoes. I lastly want to share with you a collaboration case study. I mentioned earlier that we have worked with NRDs in Nebraska pretty heavily to help address groundwater nitrate contamination concerns. One of the NRDs that we have worked with most closely is Central Platte NRD, and this has been in a few different ways. Initially, CPNRD supported on-farm trials in cooperation with the University of Nebraska-Lincoln from 2018 through 2022. Through this process, they were helping to identify producers, could be cooperators for these trials, procuring equipment that could be used to help manage these trials, and they were active in ensuring that data was being collected in a way that could be used to communicate and educate growers within the district. They also helped to host small cooperator meetings with that select group of cooperators that were performing trials within the district. They provided feedback on the technology, specifically certain elements of the technology that would have to be built or improved in order to scale the technology and meet the needs of growers within the district. Ultimately, this trial work and the effort that was put in supported the development of a new state standard for nitrogen management in irrigated corn that resulted in sensor-based methods for nitrogen management being the preferred way of managing nitrogen in irrigated corn, and also promoting in-season nitrogen management as the preferred mechanism for application timing within irrigated corn as well. From the trial stage, we moved into a demonstration education phase with Central Platte NRD. They've continued to provide support ongoing demonstrations since 2023. With these demonstrations, we continue to have replicated trials comparing grower standard practice versus Sentinel management. And these demonstrations are really built to help educate other producers in the district through field days, seminars, and grower meetings that are hosted in cooperation with Central Platte NRD. They've also started to use this technology to help manage input and practice trials. For example, if there are alternative fertilizers that are being sold within the district, or if there are new practices like cover crops, for example, that they are looking to investigate within the district. Technology has now become part of managing those trials and helping to understand how they are affecting the crop that's being grown over time. And this technology is also being used to communicate with other producers how these trials are performing. Beyond the trials, demonstrations, and education, CPNRD has also helped to facilitate adoption of this technology, whether that is facilitating meetings with respected agronomists within the district or that serve parts of the district, whether that is helping us to align with reporting requirements and understand what is being expected of producers within the district, specifically in these different phased areas that have different requirements for nitrogen management practices. They've implemented cost share programs that help producers to pay for our technology as they are first adopting it, as well as pay for aligned equipment or practices that help to just make our technology more effective and technologies like it more effective. They've also been able to facilitate spreading news updates for the progress that's been made towards addressing groundwater nitrate using technologies like ours. Ultimately, this has turned into major outcomes. We have 223 fields and about 28,000 acres enrolled in the district. And in the districts that are immediately surrounding CPNRD, we have had 890 fields and over 113,000 acres enrolled in our lifetime within those areas. Overall, we're averaging over a 40 pound of nitrogen per acre reduction in this district, which should ultimately result in lowering groundwater nitrate levels. And that is really the progress that we're looking for toward water quality goals. I mentioned earlier that we serve farms through service providers. We have been very diligent about building this service provider network up that we call our Sentry Network. These certified service providers are organizations that provide agronomy services to farms. Some examples of these are ag retailers, crop consultants, precision ag services businesses. We also work with seed dealers and independent ag retailers beyond cooperatives. These CSPs are trained in our platform and they're backed up by a Sentinel account manager that has deep expertise in the platform to make sure that there are multiple layers of support for the customers that are using this technology. And we do validate that our CSPs meet the following criteria, which are serving agronomy needs in season, leveraging data for agronomic decisions. So they're actively incorporating data within those in-season agronomic decisions that they are making. They're focused on farm profitability, and ultimately they also are aligned with protecting our natural resources, which aligns with the original part of the mission of improving water quality and improving land stewardship while also supporting farm profitability. To get started with this technology, it's really easy. You can create an account on our website if you would like, and in the system directly. You can find your CSP. We do have a URL that I've listed there on the screen to see who your local CSPs are. Certain areas don't have a ton of CSPs right now, and in those cases, it's best to talk to our team. We have multiple ways to get in contact with our team, whether that's going to the Contact Us page on the website, where you'll find emails and phone numbers for our account managers and customer success professionals. You can also email us or call us to get connected directly with us if you would like. So that is our technology, how it has performed over time, and how we have worked with farms, agronomists, and conservation districts to implement the technology successfully and what it takes to get started. I don't know if there have been any questions on the chat, but would love to take any that y'all might have today.
No questions in the chat, so just feel free to unmute yourself and ask any questions that you might have. Well, if there aren't any questions, I'll be sure to share Jackson's contact information if anybody would like to reach out afterwards. Thanks everybody so much for coming today. I hope you all enjoyed the presentation as much as I did. Thank you, Jackson, for sharing with us. And everybody have a good rest of your day.
Thank you, Lane, and thank you all everybody for your time.